see this later.
Yeah.
Okay, so welcome everybody. Guys and girls. Well, we will now give a session about wind power. Edu, who already gave some speech, some talks the last days, and me, I was not during the last days. I'm Kevin Schönleber. I'm from Germany normally. Well, normally I'm from Germany. I'm living here.
Sometimes you are not.
But I'm now living here doing my PhD, industrial PhD in Alstom Wind, which is wind turbine manufacturer. So hopefully I can answer you some questions about wind power if you have some. And we will start right now with a short video. So we will have now 1.5 hours YouTube session, which is quite nice. Okay, let's start this. It's maybe related somehow to Germany as well, unfortunately. Okay. Can you imagine what's that? What was that?
That was a bomb.
It was a bomb, exactly. Why I'm showing a video about a bomb? If I want to talk about wind power.
They want to put the what do you call it? The pole for the offshore wind power into the bottom of the sea, and there was a bomb next to it.
Okay, exactly. That's what happened. Well, it's not that uncontrolled. What happens if you want to install an offshore wind power plant before they make some seabed survey, and they have to look if there are bombs? And if there are some, then they have to get them out of there. And it's quite extensive work, which is done in every project. So, for example, I was just reading. Well, it's often in the news or the wind power news, and I think last wind farm in UK it was 45 bombs in the whole area. So it's part of the project, and it's a big issue. Okay. Just going through the agenda. What we will do, we will show. Well, I will start. We'll have a second introduction about offshore wind power. Then we'll think about, or we'll talk about the evolution of wind turbines, a bit about history, different types of wind turbines. Then I will talk a bit more about offshore wind power plant, and then we'll have some short characteristics of research topics we are looking at, and we could also develop your master thesis if you come to Barcelona. So I'm starting with this. Okay, again, Germany. That's where I'm from Mannheim, Germany. Is somebody here from Germany? Good. Where are you from?
Stuttgart.
Super. No, I don't know. Yeah, it's good. Okay, you did your bachelor in Stuttgart? Okay. So I did my bachelor in Karlsruhe, which is quite close to Stuttgart. And the other location I printed here is Fécamp in France. And this is where Alstom will build one of the offshore wind power plants. And I want to show you a comparison. So, okay, this is Mannheim. Mannheim is supposed to be one of the most beautiful cities in Germany. Correct me if I'm wrong. It's not the case, but it's nice. And here you see the beach of Fécamp, where they will build an offshore wind power plant 10 kilometers to shore, so you can see it from the shore, which is not always the case. Just to compare, let's see the difference between these two locations. We have here in Mannheim, it's the same scale. Here you see the. Shouldn't I cross this maybe? Or?
You have a pointer, a laser pointer if you want, I think.
Yeah, but I don't like this. Okay, so here you see the small village of Fécamp, or small city, and here the area where the wind farm will be built. So on the other side you see Mannheim, which is maybe this circle, and here you have a power plant, which is a coal-fired power plant, and we see that the area of the wind farm is almost whole Mannheim. And that's the reason why we go offshore, because it needs a lot of space, because the wind farms, there are single wind farms, and together they build a large power plant. And they have to be spaced in order that every wind turbine gets some wind and can produce power. So this power plant in Mannheim is called Großkraftwerk Mannheim, and it's a steam power plant, but fired with coal. It's 1.6 gigawatt, and if we compare the area which this power plant is occupying, we see that it can be 2.8 gigawatt per square kilometer. So it's a high power density. I'm not looking here at the coal mine, which is somewhere which is also occupying space, because you should also see that. But the offshore wind farm is a lot less. So we have here 500 megawatt plant, and this is about 8 megawatt per square kilometer. So it's a lot less. That's the reason why we go offshore, and that's the reason also why we need a lot of space offshore. So, but at the same time, if you see, okay, I will just test them. If you see the emissions, of course, coal-fired power plant has a lot of CO2 emissions, and the wind power plant has a lot less. Why there are still some emissions for wind power plant? I mean, to build it, yes, and also installing logistics and so on. So there are still emissions, but it's a lot less than for a coal-fired power plant. What else can we see? Then the offshore wind power plant will be built in an area where there is no load. Paris is quite far, and this small city doesn't have 500 megawatt of consumption. That's a good point about coal power, these centralized power plants, like nowadays, that you can build them right next door and just have electricity next door and feed the loads. That's why we also need some grid connection, which we will talk about later. And you already heard yesterday about HVDC, so on. Okay. What else?
The receiver is there, I think. So.
Where?
In the computer.
Okay. So now I gave the short introduction, and Edo will talk about different types of wind turbines.
Can I just ask something that I got curious about seeing your
Okay.
But it's not really related to this exactly.
Tell me.
It may be a stupid question.
It's
but
not a stupid question.
We see there that the offshore wind turbine will be built in French coast, right?
Yes.
What happens if there are some good resources in international waters?
Mm-hmm.
Whose project would that be? You know? Because in Europe your coast is really close,
Mm-hmm.
yeah. So you have countries and countries, and there are just a small scale of international waters, and you can build there an offshore wind farm and still transmit this power to the load. So how would that be? Whose power?
Who's owner of this? I think nowadays it's not a real problem, because first we try to build offshore wind farms as close as possible.
Yeah.
This could be restricted by nature reserves, other things. But probably once all the coast is filled up with offshore wind power plants, and if we then still need more power, then this will be a discussion. But I think it's more a legal discussion than. I think from a technical perspective, I don't know. But you can also.
I got curious because of the wind the wind farm just like goes straight at the line of international water. So,
but I think this is the 12-mile zone, and then you have another zone where you can, which still, it's not directly like free international water. I think there's a 12-mile zone, and then there's some, but I don't really know about this.
Okay.
Is that line? That's the continental.
I think it's a 12-mile zone of.
But it's the continental. You know,
The platform.
ocean floor. Is it closer to the surface? Because if you go far away,
It is like 50 meters in the North Sea or something like that, I think.
It depends. First of all, we try to build wind power plants where you have like sandbanks, like not a very deep water. The water depth should be as small as possible, because it's cheaper as well. So this is also something about international water, but there will be also floating wind turbines and we'll see.
How do they come up with the CO2 emissions from the wind turbine? How do they measure it? Because there's like no.
Well, it's a calculation I took from a report from some United States energy agency, and well, they look at installation cost, logistics, and then make the measurements. If you want, we can see later if I can pass you the link. And
Okay. So I will do an introduction about different types of wind turbines. Have you ever heard about the different topologies? The type 1, type 2, type 3. So I will try to go fast. So how I started, how the wind industry started. So they wanted to build reliable machines. They wanted to prove the concept back in the, I would say 80s, 70s, something like that. So they wanted something which would work. They didn't want it to be innovative. They wanted something which is robust, just to put a wind turbine somewhere and to produce some energy, right? So there is, this concept is quite simple. So here you can see that you have the blades, you have an axis, a shaft, a gearbox, and then a squirrel cage induction generator, conventional one. It is the cheapest one, the most simple one that you can find. So, and I have included like an advantage, the straightforward control. You cannot even control almost anything here because it's operating at fixed speed, okay? But this concept, they have, this thing have different drawbacks. One is that you cannot optimize the wind power extraction, right? Because if you are rotating at a fixed speed, you cannot adapt to the wind speed of the wind turbine. So that's a main drawback, okay? Another important drawback is what you can see here, that the squirrel cage is connected directly to the grid. That's why it is rotating at a fixed speed, right? Because it is imposed, the frequency is imposed by the grid. And this is another drawback. This is because if you have a eventual grid fault somewhere, or have a short circuit in the grid, this wind turbine will see a short circuit, and the turbine will see like a decrease on the voltage at the point of common coupling of the system. So here you will see that the voltage is going down, and if you are extracting some power, if the voltage goes down, that what you will see is that if the power is the product of voltage multiplied by current, right? So if the voltage goes down, the current will rise up fast, okay, and then it will trip. The problem with these things is that as soon as they have a voltage sag, they tripped, and they could even this can be even more dangerous for the system. So as soon as we had more and more I would say wind power installed, we started to see that this kind of configuration could be the transmission system operators forced the technology to evolve to another different topology that has power electronics, okay, that can, for example, at some point during a voltage sag, support a certain something on that gives some grid support there. Okay, there is another similar concept to this one, which is the, well, just a picture. This, yeah.
What do you mean by soft starts? In the previous slide.
This one?
It says soft start is required.
Yeah, because this is for just for grid connections issues. You know, if you connect, for example, you start. If you connect directly the converter, the generator directly to the grid, maybe you could have like 7 times the rated current flowing through the circuits. So you
mean like a normal motor, right?
Yeah. For example, yeah, it is like connecting a classical motor directly to the grid. So you need something there to limit the current that is flowing through the circuit on the first, I would say, seconds or milliseconds. Okay, that's the main idea. So then this is an ecotechnia. So this is the old Alstom bought ecotechnia. So this is I think that they started in the 70s or in the 80s, I think, something like that. And they started building. This is a Spanish company which is here in Barcelona, and a few years ago Alstom bought this company, and now it is Alstom Wind. So this is an example of the thing. Okay. Well, what is called Type 2? So Type 2 is limited variable speed. This is a concept proposed by Vestas. It is called also OptiSleep back in the 90s. So the main difference between this and the previous one is that you could move. You have a range, a speed operation range. The other one was operating at fixed speed, and this one is a bit different. You could move the operational speed between 0 and 10%. How can you do that? Here you can see that the generator is a one rotor induction generator. So you're including some resistors there on the rotor of the generator, of the induction rotor, and then with that let's say resistors, variable resistance, you can optimize a bit more the wind power extraction. But it is also limited. I mean, the range is quite narrow, so you cannot really move far away from the operational point. And as you can see, it is exactly the same concept connected to the grid. So it is directly connected to the grid. So the only benefit that it had is that you could optimize a bit more the operation, because you can vary a bit the speed when you're operating. But it is not possible, for example, to grid support and any other stuff like that, because you don't have any power electronics or any controller for that reason. So, yeah.
Even if you have a good optimization with this kind of generator, don't you have more losses?
Yeah, of course, but this is maybe the losses that they have on the resistors. You can extract more power than, for example, operating with a squirrel cage. You can imagine that the squirrel cage is operating just as a fixed speed, so probably operating at I don't know, it depends on the pair of poles, okay? But if it's operating at 1500 RPM, it could be producing less energy than, for example, this concept, because then you can vary the speed. Okay, you are having some losses on the resistor resistances, but you still produce more power. So then they were playing with this thing. Okay. Yeah. Okay. So as I said, having this thing connected to the generator, directly connected to the grid, were causing some trouble during voltage shocks. And also, you could see that the optimization of the wind, of the wind power extraction was not that good, because we cannot really vary the speed. It is a limited range of speed. So what they decided to do is to include, this is a picture of Vestas, okay, who proposed this concept. So we moved to Type 3, which is the classical doubly-fed induction generator-based wind turbine. So here you can see the concept. It is again a one-rotor induction generator, but in this case, instead of installing resistances on the rotor, okay, they were doing they changed the concept to install a reduced scale back-to-back converter here, And here you can see that the stator of the machine is connected directly to the grid. It was still connected to the grid with this concept. It is still connected to the grid. And then you have the rotor connected to the grid through a back-to-back converter. What happens with this concept? I mean, this back-to-back converter allows better power extraction from the wind because it allows to vary the speed. Okay, so it is like, I think that it's around -40 or to +40 of speed variation. From the base speed, which is the synchronous speed. Okay, we have of course active and reactive power control, and this is probably the most wind turbine this is the workhorse of the wind industry. Okay, so it is the most installed wind turbine everywhere. Okay. Well, what happens with that? So here you can see that, for example, in case of a voltage sag, of course that we have still the stator connected directly to the grid, but we have the rotor, we have this converter, but that we can do something there to prevent our machine from disconnection. Okay, and even we have a converter here connected to the grid, which could, instead of tripping the whole wind turbine, we could give some grid support, as for example, I don't know, injecting some reactive power in case of faults. Okay, that typically TSOs require that to wind turbine manufacturers, right? So, well, it was a game change at that time, and it is still the preferred option for offshore. And here you can see that the main drawbacks that this thing has is that you need slip rings. You have gearbox with, the gearbox is always a main. There are some important failures and downtime costs attached to the gearbox. Also for maintenance for the slip rings also. And the control is not that easy compared to, for example, something like which is the Type 4, which is the full power conversion system, which is all the full power converter is when you have all the power flowing through the converter, not just a partial scale converter. Okay, but this was so appealing because the converter, installing a reduced power converter, it is rated to a 30% of the system. You could reduce the power electronics, and at that time when this thing started were a bit more expensive than today, so they chose that option because they could allow the installation of these things with a relatively reduced cost. Okay, and then, well, this is a picture of Alstom Eco 100. This is the proposal for Alstom for this type of generators. And then the Type 4, with Type 4 we have many different proposals, I would say. Okay, which is Type 4? Type 4 is, as I said, having the wind turbine. You could have or not gearbox, okay, and then you could have different type of generators: wound rotor, synchronous generator, permanent magnet ones, squirrel cage induction generators. Okay, it depends on the manufacturers, they choose from one or another. And then you have, what you commonly have is a full power converter. Okay, so you are using all the energy is going through the grid through this power converter, and through this power converter you have completely isolation from the wind turbine side and from the grid side. So, for example, in case of faults, it is something that, first of all, it has, let me tell you that it has variable speed, completely control of the speed, so you can optimize perfectly the wind extraction. This is an important point. And secondly, as you have completely, let's say, isolation between the wind turbine and the grid side, you could provide, you have fault rate through capabilities, so you can remain the system connected even in case of faults, because you can isolate the wind turbine from the grid. Okay, you can of course control active and reactive power. You can perform like grid support. You have grid support capability. You can inject reactive power you like, voltage control, even frequency support if you want or you are required to. And well, basically this is the concept. And now I'm going to show you the different proposals of different manufacturers. Okay.
When you say that you
Yeah.
can control reactive power,
Mhm.
I mean, can you produce reactive power with a machine that is not a synchronous generator?
Yeah, I mean, you can produce reactive power just with this grid side converter connected to the grid. I mean, the reactive power is not like active power; it's another different one. So it's this: you can inject or absorb reactive power just with a conventional voltage source converter. You know what I mean? It is. I mean, this side. You have to imagine that this side is an AC side, which is operating at a whatever frequency it is rotating the machine. So if you have a synchronous generator there and it is rotating, you know, at I don't know, let's say 18 RPM, you have a gearbox, so the generator will be rotating around, for example, at 1500 RPM. Okay, but you will have here a certain frequency, but you have DC in the middle. Okay, so if we are rectifying that DC at that AC power, then you have DC and you have another inverter to inject the power to the grid. Okay, but this is doesn't have. I mean, the active power is totally independently controlled from the reactive power. So you have active and reactive power independently controlled using this VSC technology. These converters are VSC technology, so they are based on IGBTs. Okay, so you can inject I mean, it depends on your converter capability. Of course, you will have a converter, for example, rated for 6 kVA, something like that. Okay, so yeah, it's a kVA. Sorry. So if you are injecting, I don't know, a certain amount of active power, you will only be able to inject, you know, a certain amount of reactive power, but you are still able to do that.
Are there also approaches to connect the DC output directly to an HVDC link for offshore?
Yeah, I think that Kevin will give some ideas about that, but there's also what it's called DC collection grid for this is being proposed for offshore wind. So you will have, as soon as you have here an AC to DC converter, then there are proposals for installing DC-DC converters to step up the voltage and then transmitting the power for, you know, using an HVDC transmission.
Why hasn't this been realized yet?
Well, I think that it is a matter of cost, I think. I would say before that, because, for example, there are not, first of all, there are not so many HVDC links. Okay, so if you don't have an HVDC link, I mean, if you have an onshore system, you will definitely go for this topology. Okay, so you will invert again to the AC, put a transformer there, and that's all. But if you have an HVDC link, I mean, now, as you say, everything is in the research stage, so there's nothing installed like that, and even there is not a clear answer about which are the best DC-DC converters to be installed in these kind of things. I mean, there are proposals of you know, connecting turbines in series to have a higher voltage with a DC-DC converter to have isolation, then to gather several outputs in DC of several wind turbines and then elevate the power to a higher voltage. But I'm not sure. Are you talking about this?
Yeah, we can.
So we can
have a short talk about
your thesis is something related like that. So yeah, he can explain better than me for sure. So, but yeah, right. It's an interesting idea. Yeah. Sorry.
Are wind turbines construction topologies are settled or it's still in development? The focus is more about on control, or maybe wind turbines as a topology or construction is still developed, or
what do you mean in
the construction of the wind turbine? Like, let's say this it should be maybe bigger, or we should have those wings on the different angle, different construction. Is it still on on the table? We still develop it. It's like settled. Few constructions for few different.
Well, I would say that for offshore, I mean for offshore industry, for onshore industry, the doubly fed was so extended, and everybody was installing doubly fed induction generators, or I mean Type 3 wind turbines. I think that only Enercon has well, and some other people has permanent magnet synchronous generators based machine. I mean, every manufacturer has different topologies and proposals. I think that everybody's going for a 3-bladed, or most of the manufacturers are going for 3-bladed, and then you have also variations on the gearbox. Some people are installing a multiple stage gearbox. Other people are installing a single stage gearbox with medium speed generators. I mean, it is still evolving. It is still evolving. Also, I think that Vestas is going in that direction for offshore wind, and I think that as soon as we have decided to go to offshore wind, new topologies have been released by manufacturers. So I think that this will keep changing, and there are some new proposals like Type 5 wind turbines, which I don't know anybody that is installing that, or even I don't know if somebody has proposed that, but it's something new. So it is still evolving. No, it is not something in steady state, I would say. Yep.
I have a small question about the fact that the blades can rotate around their axis.
Yeah.
Is to keep the speed constant? I mean, the rotational speed constant, or is to keep the power constant?
No, this is basically it's called the pitch. For example, it's called pitch or stall. What is used nowadays is the pitch control of the as you say of the blades. So this is basically used for when you imagine that you are operating at rated speed of the machine, so that your converters are extracting the maximum power that you can, and you are, for example, I would say at I don't know, 13 meters per second, something like that. Okay, so imagine that you have an increase of wind power, but you cannot really extract that because you don't have available capability on your system, right? So you cannot really extract 8 megawatts from because you have the thing rated for 6 megawatts. So what you will do with that is you will rotate the blades in order to lose some energy extracted from wind. Typically you have the blades which is called at 0 degrees, something to absorb the maximum power from the grid. And as soon as you want to limit the power, you rotate a few degrees the blades in order to lose some.
So these power get wasted.
Yeah,
not used.
Yeah, because you don't have the capability to extract it. Of course, if you have an overrated machine, for example, an overrated generator and an overrated converter, you could do that. And I think that in some cases, for a few seconds, you can handle in some machines like that they are rated for 6 megawatts. You can handle like 7 megawatts transiently, but not in a steady state because they will burn the.
So this means that even with this configuration with all the power electronics behind, you still have to rotate the AI.
Yeah, definitely. Yeah, you have to, because otherwise
I thought it could be just a matter of induction machines, so they didn't want to. You cannot vary the speed, rotational speed very much, so you had to vary the rotational angle of the axis of the blades. So but it's still like in all the configuration, the blades are moving, right?
Yes. Well, in the older version it was not like this, but nowadays everybody is because you rate your system for a certain amount of megawatt, and all your system, also the structural system is rated like this. So if there's a storm or a very high wind, you only get some power out of the wind. But otherwise it would be very costly to build a wind turbine which can operate at all wind speeds which will happen in this location. So it's a trade-off on cost.
Even for high wind speeds, I think that it's they're like a survival speed, right? That everything is rated for, even when you. It was surprising for me that when in a really windy day, I was driving somewhere and I could see that all the wind turbines were stopped, and I was wondering why. So there is like a maximum speed they can start pitching the blades, I don't know, at 15 meters per second or less than that, until a certain speed, that it's 25-30 meters per second, that they trip the whole machine. Because they have to stop, because otherwise they will, break something.
Will destroy the machine.
Yeah, and then what they do is they disconnect everything and they pitch totally the blades in order to not absorb any power from the wind. That's what they do fast,
Okay.
So the pitch is also used to start the machine. So they start rotating the thing, moving a bit the blades from 90 degrees. I would say they start pitching until they can start the whole stuff and start moving it. Okay. So this is the newest concept, I would say. I will show you different. I would say different generator concepts. So the first one is the squirrel cage induction generator proposal. This is proposed by, I think that Siemens has this technique. So here you will see that the concept is exactly the same. It is what is called type 4 variable concept, but only changes the generator, and in some cases you will be able to avoid including a gearbox. Okay. So here, what are the advantages of this thing? You have a really simple generator. You have, you cannot really avoid the gearbox, okay? Because you cannot really build in a large number of poles. You have to remember that if you can do a large pole machine, you can reduce the synchronous speed, right? So then the gearbox can be small. So with this case, you cannot really build that, it's a manufacturing thing, or how the things are made. You cannot really build a squirrel cage induction generator with a large number of poles. Okay, it's not possible to do that. Okay, so it has. I have included like relatively low efficiency of the system. So you have the generator, which is synchronous generator have a higher efficiency, and that you have the gearbox losses and even maintenance failures and other stuff like that. Okay. Well, this is something proposed by Siemens. Then you have another different concept. Instead of an induction machine, you have a synchronous generator. This is wound rotor synchronous generator. So you have the rotor controlled by a converter here. I have included this here, and this is connected here, for example, here to the DC link or even to the grid with a rectifier. Okay, and with this thing, you can control even the machine, and you still have this full power converter version. Okay. What this thing, it is interesting. So you have, again, totally variable speed, and the interesting part here is that you can build a large number of poles generators. So you can increase the number of pole pairs. So then you can decrease again it is a matter of increasing the generator because you will have a large number of poles there, but then you can avoid installing the gearbox. Okay, so you avoid the cost of the gearbox, and then you avoid the maintenance feature and all stuff like that, and the downtime failure associated cost. Okay, but on the other hand, you have a heavy generator because you have more iron and copper there because you need a large generator, and that's probably the main failure. You have, of course, rotor excitation losses, but they are not that much. Okay, and of course you need the slip rings because the rotor is rotating, so you need to create the feel of the rotor of the synchronous machine, right? So who proposed this concept? This has been basically proposed by Enercon. This is one of the latest machines, but they have been installing this system for a while. So here you can see that in the nacelle. Here you can see that it is a bit it's wider, so they have to include the generator, the multipolar generator on the nacelle, so they have to fit it here. So that's why they have these large nacelles, and they look a bit different. They are not that ones that are long and squared ones, so they can change a bit the thing. There's something interesting about it. I've read. I think that it was a press note that they of Enercon that they were stating that they could potentially go to offshore, but I think that they are not right now. Correct me if I'm wrong, but they are not going for an offshore prototype. Maybe it is possible because they decide not to go to offshore because they could have a heavy generator and probably the structures are. For example, the permanent magnet ones are lighter, so probably that's the reason why they are keep staying on shore. But I don't know. Well, what else? We have a synchronous generator. The next logical step is to say, okay, I have a large synchronous generator with excitation and all those stuff like that. Why cannot avoid all this stuff and include permanent magnets to create the field, the rotor field. So there are some proposals on that. What this thing allows is to also reduce or even eliminate the gearbox here, because you don't have to include any gearbox, because you can create a large multipolar permanent magnet synchronous generator, and then you can reduce the synchronous speed or the speed of the low speed of the shaft, of course. Okay, and this is something which is interesting. It has a higher efficiency than the previous one because you don't have to excite the rotor. Okay, you don't have to create the rotor field because it is created by magnets, and even you can have a lighter and smaller generator because you don't have to have that coils to create the let's say the magnet of the rotor, right? So you have just magnet installed on the rotor surface, which is not easy to do, but this is something interesting. Of course, this has some drawbacks. The first one is that it's a bit expensive to buy this. I think that the magnets are neodymium ones, so this is not cheap, of course. Then you don't have any possible type of control on the rotor excitation, so you have a permanent magnet there. So it's not possible to do anything with the rotor magnets. You have a magnet and there's a constant flux there, so you cannot really reduce or increase the voltage. So you don't have any control capability on the generator. So you just can control with the machine side converter. And well, you potentially you have in case of an eventual short circuit, you have if you have a short circuit in one phase, this could cause that large current flowing through the coils of the stator could demagnetize one of the magnets, and then this could cause a failure on the system.
Why with the synchronous motor you can have a larger number of poles than the induction motor?
Yeah, that's a good question. Yeah, I think that it's a matter of how it is built. I'm not sure on the squirrel cage induction generator why, but I think that it's a matter of the flux and all stuff like that. But in the on the permanent magnet generator, it's simple to increase the number of poles. It's just including, instead of north-south on the rotor, it's just doing it many times, right? So this is simple. On the other hand, I think that it's a matter of how you can imagine a large number of poles on a squirrel cage, because it is well, typically the smaller ones are aluminum core. I don't know the huge ones, but you have like a squirrel cage there, so it is weird to imagine that with a large number of poles. I don't know how can they do that, but I have not seen this without. I think that it's not physically possible, but I don't know exactly the reason why.
So with an induction motor, you can't avoid to have the switchgear.
No, the gearbox. Yeah, you have definitely to include that. Yeah, all the proposals. I think that Siemens, they are always they are the ones that propose this system, and they have to include the gearbox. Yeah, any other question? Okay, so this is the direct driven topology, and there are, I would say, two different ones. One interesting one is with a single stage gearbox. So you have, instead of going for a large multipolar machine, you have you create a machine with a less number of poles, not that large number, but it is still large, because you need you still have a gearbox, but it is a single stage, so the ratio between the high speed shaft and the low speed shaft, it is reduced, it is limited. Of course, the typical ones are planetary ones or episcodal ones, which have a certain number of stages, and they could reduce like 1 to 74, something like that. With a single stage gearbox, you could not reduce that much. So this is another proposal, interesting proposal. I think that Vestas is proposing that. And well, basically, you are including a gearbox, but it's not that complicated. Okay, so maybe they have less danger of failures there, and you can reduce the cost of the generators because you don't have to do a larger generator, of course. So that's a good point of that. And then you have, which is exactly the same concept, but including different multiple stages, like 2 stages or even more stages. Then you can reduce even more the size of the generator, so the generator is cheaper, but you have to include the gearbox. For example, Gamesa, I think that they have this this thing installed in Canaria, in the Canary Islands. So they say that it is offshore, but I'm not really sure that this thing is offshore. So well, it is quite close to the shore, but not really. So well, yeah, they are testing it at the moment. So maybe it's the perspective, right? So they have this thing behind. So I don't know if it is installed offshore and this is a matter of perspective of the photo or not. But anyway, so well, this is a 5 megawatt peak wind turbine. So this thing is. I think that it has two-stage gearbox. Okay, even with that, it is a medium speed generator, so it has a higher number of poles compared to the conventional ones, but it is not, for example, that much. Okay, and then this is well, the one of the most interesting concepts, I would say, or the newest ones for wind turbines, for offshore wind turbines, which is we call it multiple three-phase machine, where you could have a different number of stators there embedded in the same yoke. You could have in the same stator, so you could have, for example, 2 or 3 stators in the same machine. So it is like having 3 different machines in the same system, and this is interesting in terms of basically redundancy. So here, for example, if you lose one of the converters because if you have a burned converter or something like that, you still have 2 or even 3 remaining, so you can still generating. This is done like this because, for example, if you have an offshore wind turbine, and you have to imagine that it's difficult to do maintenance task in the middle of the sea, and even to repair that, it depends on the season of the year. It is difficult because it's not easy to go there with another huge converter and replace it. So it is something that I mean, it's a matter of cost, and what you cannot do is to lose one of these wind turbines. I mean, you cannot lose a wind turbine for, I don't know, a month. Okay, because it's something that you will lose a lot of money there. So they are proposing this. Basically, Alstom is proposing this topology because of redundancy. They still can produce some power even if they lose one of the stators. Okay. Then it also has some benefits. They can reduce the stress on the power electronics. You have to imagine that if you have only one converter, all the current should or must go through this path. But if you have different power channels, you can reduce the rating of the IGBTs there, or the rating of the converter, and you can, instead of having one large converter, you could have 3 different smaller ones. Okay. This proposal is also direct driven, so here you can see that there's no gearbox here, so you can even install a multiple 3-phase machine or a 9-phase machine, for example, in the case of Alstom, with I would say with no gearbox. You can do a large multipolar generator, of course. Okay, so this is something that it is also interesting. That's why this machine looks like this. Here you can see that it is not again it's quite similar to the Enercon one because they have a large number of poles. So you have just a large number of poles, and then you just need the converters to inject that to the wind farm within wind farm grid. So that's that's the concept. This is basically, this shape is caused by the generator stator. Okay, so it is quite large because you have to embed like a large number of poles there. Okay.
They have gearbox?
No. It is, that's why if they are, I mean, they have included this generator. Just, I think that they want to reduce the maintenance cost. That's why it is permanent magnet one also, and they wanted to increase the reliability and redundancy of the system, just to keep maintain the system working even in case of certain failures of the system. So if you lose one stator, you can still produce power with the other 2. So, okay. Any question about this idea? So, well, the Type 5 wind turbine is not something that we like because we are power electronic guys, and there's, as you can see here, there's no power electronics anywhere, so we are quite reluctant from this idea. So here you can see that this concept is, I don't know exactly who proposed this, but the main idea is to have a variable, it's called like variable speed or variable ratio gearbox. So you have a gearbox connected to a classical synchronous generator. So in as a conventional, let's say conventional, power plant, let's say. You still have some power electronics to create the field, but it's not so interesting. It is, and how this thing works. So here you can vary the speed because you have a variable speed gearbox. You have the one rotor synchronous generator connected to the grid, so it is rotating at a constant speed. And varying the ratio of this gearbox, you can change the speed of the rotating blades, right? So you can keep constant the rotation of the synchronous generator and vary the speed at the output, so you can adapt your system to maximize the power extraction. Okay, don't ask me how they do that because I don't know. So I just include this thing because I thought that was interesting for you also to know that there are some other people proposing new stuff. And here you can see that this thing has a variable transmission ratio, and the benefit is that you have a synchronous generator connected to the wind farm grid or whatever it is, and it can provide like conventional synchronous generator grid support, and it is a conventional power plant, I would say. So you have different synchronous generators connected to the grid that can give frequency, grid support, and other stuff like that.
Do you know if there's a variable speed in the mechanical side? Can it be done continuously, or is it just like stages?
I think that, no idea. No idea. I think that it's continuously. Otherwise, it should be so aggressive for the system, right? To change radically it should be smooth. I think that it is done with a third axis somewhere, which is adapting the speed to do like to maintain the first constant and the other one variable. So there's something in the middle with a frequency converter and another machine which is adapting the speed, but I'm not really sure about that. Okay. Well, any other question?
Déjalo del control, sí. Déjalo del control, es media hora.
¿No lo explico?
No.
Bueno, es 5 minutos, ¿no? ¿Lo paso rápido? Okay.
Bueno.
Sí. Yeah.
Is this actually used? Because
this one?
You don't have any pictures of it. So
No. I have not.
It's not used.
It's not used, definitely. No. It is in some papers. I don't know if somebody is.
It's relatively new.
Yeah. I would say that this is quite new. So even I don't know if you are planning to install them in some places, but it is already installed prototype, but it is something new.
But yeah, they're building this.
They are building this one, okay. But this is
it's conceptual.
It is like people keep defining types. So this is type 5, and the benefits are that you have these synchronous generators. So they are. If the transmission system operators require you to do something like to behave as a conventional power plant, why not to include a synchronous generator and keep us the thing as close as possible to the conventional ideas, right? So here you can have overloads or whatever you can do there, so you can you have more possibilities instead of having, with the converter you have also other possibilities, but probably you can reduce the cost. I don't know. It has some advantages, but it of course needs to be studied, because then it changes completely the operation of the wind farm, how you can operate that, how it is behaving in terms of faults. You have a lot of synchronous generators connected to the same point, so how the controllers interact, if they are all controlling the frequency. It's going to be interesting if this thing is installed somewhere.
Who proposed it? Number 5,
Not me.
Researchers.
Yeah, I found it in some papers, and when you go to conferences, you see some papers of some people that is interesting. I am also interested on that, but I didn't find it on the website. I mean, I checked that for 5 minutes, so I didn't look it in detail.
Maybe
but
there's somewhere a small prototype of that.
Yeah.
But it's part of research.
Yeah, and well, just to conclude my part, do you remember you were yesterday in IREC, right?
Yeah.
Have you seen the prototype that they have for a 9-phase machine? Do you saw those the two couple machines, these ones here, these ones? Have you seen it? I mean, did they did a presentation or something working on that? Okay, so
just saw like in the picture.
okay, so you just saw something like that, right?
So you see it again.
Yeah, so you will see it again in pictures. Okay, let me show you what we did with this thing. We did we were in a project collaborating with with CITCEA, IREC, and Alstom. This is something to we did that to test some new control developments on a scale platform before going to the huge one. But we are now currently we started testing on the small scale one. So we built a 9-phase generator, which is this one here. Here you can see that you have 3 sets of cables. So the one is 3-phase one. And basically you have 1, 2, and 3 back-to-back converters with the 3 coupling inductors, and this is the variable speed frequency for the 3-phase generator, which is coupled, which is acting as the wind emulator. Okay, so it is something like this. You have this is the frequency converter, which is rotating this thing here, acting as the wind blades. Then you have a generator and 3 channels for injecting the power to the grid. So how this thing was operated, this was controlled by these power converters here using DSPs. So I did the programming and all that stuff. So yeah, that was part of my thesis. And here you can see the thing, how this thing is operating. You can imagine that it was quite complicated because each of the DSPs was programmed in a similar but different way, because you have to. Each of the machine side converters have a shifting on the angle, so you can imagine that this is just 3 phases, and here you can see the picture of the 9 phases of the machine. So I'm just plotting the phase A of each stator. So I think that I ran out of current probes, so we had to buy more at that time there. So when I took this picture, there were only 3, so I decided to go for the 3 A phases of the system. So here you can see all the stators extracting the same amount of power, so that's why you see the same power, the same amplitude in current. And for example, the benefits, I wanted to include that because one of the benefits of this system is that you can operate at different rating each stator. For example, even I think that I'm not sure if the Alstom one, but you could at some point, for example, disconnect for efficiency to different stators and keep operating just with one, because you could avoid the losses of the other 2 converters. Okay, so for example, or you can reduce if you have or if you know that one converter is a bit failing at some point for higher powers, you could reduce the operating of one of the converters. So here you can see that the yellow one is operating at a reduced power compared to the other 2. So this gives you some more margin to do some stuff with the converter and with the system. Okay. So that was just to show you a bit how this thing was working.
What's better to operate? For example, if you want to decrease power, like have 2 of them at 100% and the other one at 50, or reduce the 3 of them at the
Yeah, that's interesting. We haven't checked that. So to be honest, I have not checked if it's better to. You have to do a calculation on the efficiency of the system with simulation and all that stuff. So we didn't have the exact parameters of the IGBTs and all that stuff. But my feeling is that it could depend on the operational point. At some point, probably it is better to keep just one converter operating, and at some point it could be better to have 2 converters operating at low rating instead of 1, because probably if you start flowing more power, you can. The converters typically have one steady state losses, and then they increase with the power that is flowing through them. So maybe at some point, you know, it is a matter of checking that. But I cannot tell you which is the boundaries between one operation and the other one. So yeah, it's something interesting, of course. Yeah. Any other question about these things or any other type? So well, I will let you continue.
Okay. So thank you for this nice overview.
Yeah.
So I will look a little bit about what is offshore wind nowadays. I'm really sorry for this camera. I want to be because we're talking a lot about offshore wind and it's so big and it's developing, but we should just because now I'm turning around. Because we should always keep in mind that onshore has a lot more turbines installed, because we do it for quite a long time, since more than 30 years. And just to give you some figure, well, this slide is mainly about offshore, but I just give you the figure here. It's the figure for Europe, and we have 130 gigawatt onshore and offshore installed end of 2014, and we had 8 gigawatt of that is offshore, so it's less than 10%. But just to give you the new figures, I read yesterday that now at the half of 2015 we have 10 gigawatt installed, so we had 2 gigawatt more installation. So it's fast growing, and I think in the future it will not overcome onshore, but it will be more than 10% share. Of course, onshore it's a lot easier to install, but well, offshore there is more space and we have higher winds. Now Edu presented all these types, and he said, okay, the type 1, type 2 was 80s, 90s. Type 3 is quite dominant in onshore. But when we go offshore, well, I think there are 4 or 5 manufacturers who are really in the game offshore, and only one of them is going for type 3. And probably in the future it will be quite difficult for him for them to maintain type 3, because the type 4 is seems to be a lot more reliable, and it's so important offshore, because you have to the best thing would be we go there, we install the turbine, and then we are waiting onshore 25 years extracting power. It's not like this, but you see the point. You want to avoid to go there 5 times a year. You want to go there only 2 times a year in order to do some maintenance, because it's very costly, and what also Edo mentioned, you can't go there every day, because of course you try to install it in a windy region offshore in the North Sea, and so you can't go there with a helicopter, you can't go there with a boat, the waves are too high, and so on. Just to give you some figures, offshore the power rating of the turbines is increasing a lot, and that's maybe also a question. I think in the last row on the right you asked if there's still development in the turbines. Of course there's development. I mean, I think also car industry is developing all the time. But as Edo said, 3 blades nowadays is state of the art. You don't try to have a higher tower, but if you want to extract more energy, you have to increase the size of the blades, because you want to sweep a large area. Mm-hmm. And then, of course, at some point you have to increase the tower size, because otherwise your blades are scratching the ground, and that's not very good. And now we see individual turbines which are 6 to 8 megawatt offshore. Why do we don't? Well, Anakan also has some very large turbines onshore, But in general, turbines onshore are more around 3 megawatt, because this seems to be like the most cost-effective point onshore. Because there's some, for example, also some facts about logistics onshore. Of course, if you go offshore, you can build your plates and your tower in a factory which is close to a port, maybe, or is a port itself, and then you can just put your plates on a ship and ship it out. Onshore, there's the problem that you have to carry it on trucks, and if you want to pass a bridge, there's the limitation for the blade in terms of diameter of the blade himself. So not 80 meters, but 5 meters of diameter of the blade if you look from the front, because you can't go through the bridges anymore, or below the bridges. So it's quite complicated, and that's what I'm saying. Okay, logistics are less restrictive, but doesn't mean that it's easy, because putting them on a ship and then build them offshore with a crane is not that straightforward like onshore. Here I will need your help. It's about how to interconnect the turbines. We can look at 3 topologies. I just printed here 4 turbines, but it can be also 7. And we want to couple it to this point of connection here, and we can have individual cables from the turbine to the point of common coupling, or we connect them in a radial form, or we have something like a ring. So we'll just go through here, and you will answer me the questions. Well, you don't answer the question, we can discuss how we have to fill this table. And we'll start with redundancy star, just in comparison to the other topologies. What do you think?
Yes.
How redundant is it?
Top.
Which one?
The star topology?
Quite redundant.
It's quite redundant, because every turbine has its own cable, and well, if one turbine fails or when one cable fails, the others can still operate. So high or top. Then the radial in comparison to the ring. It's low. Yeah. And the ring a little bit higher. If you of course only if you size this cable to be able to export all the energy, because otherwise then about cable ratings. So I mean, you know, the cable, the larger the cross section gets, the more power it can carry. How do we have to size the cables here for the star? Small, just the power rating of the turbine. For radial, yes. Sorry, can. No, yeah, I think you're right.
Depends on which point of the connection. The furthest one is small and.
Exactly. That's how we can do it. We can have different cross sections, and then for the ring. Yes.
So you guys are screwed, yeah.
Sorry?
I mean, if the first line and the upper side fails, all the power will have to go through the other.
Yes.
So you have to design again high, right?
Yes. If you want full redundancy, you have to full redundancy. Yeah, you have to design it like this. I will same as the feeder rating. And the total cable length, well, this is not so easy maybe, because you don't know the positions of the wind turbines, but just from this picture, what do you think? Where is the total cable length the highest? For star, yeah. And the lowest? And then for ring, okay. Longer than short. Okay. So what would you build? You prefer the ring?
Yeah.
Okay. What the others? Somebody wants to go for star. Somebody wants to go for radial. Somebody for
Well, star is super reliable, and since all the turbines are, I want all the turbines to work, and it's hard to get there to do maintenance. So reliability is important, and if the bus is close to the turbines, why not to spend a bit more in cables?
Do you know how much cables cost?
Yeah, I think about 500,000 euros per kilometer.
Yeah.
The installation.
It's more or less like, yeah, could be like this. Maybe for medium voltage a little bit less, but
Oh yeah.
yes,
Fine.
it's quite expensive. So what developers do, they go for these two options. And of course, sometimes you have a very small radial. That's what you're saying. If the PCC is quite close, then you can also connect only one turbine to this. But in general, we have radial and ring structure. And for the ring structures, mainly that this closing ring here, this one, is not rated at full power. So the reason is that we want some redundancy in case of failure, but only to energize the turbine, because the turbines, they need some energy in order to operate, and they're trying to do this in order to avoid that on each turbine there's a diesel generator which you activate, or a battery which you activate in case of cable failure. Okay, then I have here a layout of some offshore wind farms. So it's the wind farm I showed in the beginning, and it's what I said, 500 megawatt. Okay, you already saw the area, which is quite big. I think I made a calculation. How many football pitches it was? 9,000 or something like this. It's huge, because you have to see that the turbines are spaced like around 1 kilometer, and if you have 80 of them, it's quite a big area. So you have here.
This is one radial, circular.
This one is radial. Yes, they were not going for ring connection, but yeah, it's radial. But you can see other projects at the moment which are ring, and I think it's getting more and more that developers go for ring.
So they do like radial and then start the bus.
They just close here the ring, so you don't need a lot of more cable, and you have this on a small power rating, and then you can just energize the turbine in case of the failure of the ring.
Question: how about the wake of the wind, right? Because some turbines produce less wings depending on their position. Yeah.
Produce less energy. Yes. For
Yeah.
the wake effect, you're referring to this.
Yeah. So
Yes.
the rating of the cables, it goes into this equation or not?
No, because according to my knowledge, I would say no, because if you have high wind, if you have the rated speed of the rated wind speed when turbine is producing full power is, for example, 12 meters per second. Due to wake effect, you have a reduction. Okay, what is wake effect? Wake effect is when the wind is coming from here. This turbine gets the full wind, and the turbine which is behind it is not getting all the wind anymore. It's like in Tour de France when they try to catch up behind each other in order to. Here, the second turbine doesn't see the same wind, so it produces less power. But this is only in partial load. So if you have 15 meters per second, the first turbine sees 15 meters per second, the second 12 meters per second, then it's still at full power. So you have to rate your system at full power.
Is this, sorry Kevin, is this a real layout or?
Yes, this is a real layout. What you also see, you have only two cable types. What we were saying before, for the radial, we can have in each section another rating. Why do they use only two cable cross sections? I mean, this cable cross section is the same like this, but this cross section or this cable has to export only one turbine power, and this has to export 4. So they are rated at for 4 turbines. What's the reason for that? What could be the reason?
Maybe there are conventional cross sections.
That's one reason, yes.
And
It's standardized. Sorry?
And there is a length of typical length of cable, and you just
The cables you can ask the manufacturer to build them of all the lengths you want. But there are standardized.
When they lay them, the
process.
cables, maybe it's easier not to interrupt, and so they can lay continuously the same type.
That's also the reason, because anyway you have to you connect your cable to one turbine, then you have to go down to the ground, and then you go up in the next turbine, you connect it to the bus bar, and then you have a new cable connecting. And so that's you can't do the continuous thing, but there is some installation. Think about you have to install only 2 cable cross sections. Maybe it's easier if you have only 2 types. But the main reason is economics. Your how do they call it? It's not sales department. The procurement department. They want to sell only. They want to buy only 2 cable cross sections, because they say, okay, if I go to my supplier and I tell them I want 100 kilometers of that and 50 of that, he gives me a reduction. If I want a lot of different cross sections, it will be a lot more expensive. That's why usually, and you will see it in all the wind power plant layouts, there are only 2 or 3 different cable cross sections. It's very rare to see more.
By the way, there is a distance between 2
It's-
generators. It's like you told kilometer, yeah.
Yeah, it's around 1 kilometer for this.
Yeah.
Normally it's, I think it's 6 to 9 times the rotor diameter. Or
And this
plate
is
length.
enough to avoid this weakening of the wind.
No, well, in this configuration probably they will have some. We also made a test and they will have some wake effect here,
We will,
which is coming from here.
Is it a huge effect? Like it's
At partial load, it's a effect, so you reduce by
so
some meters per second. Some, yes, so
to
1, 2,
to
3.
Oh, so okay. I wanted to ask then if the weakening is a big one, do you place a different wind generators? But if it's only a couple of meters, so it's probably not necessary. You just place all the same.
It's all the same. Because also from economics perspective, it makes no sense. Normally, one wind farm, if it's one wind farm is if it's constructed at the same time, then it's with one turbine type. Okay. Then for grid connection, maybe you saw. Have you already seen something about that? AC connection, HVDC connection. I don't know if they were talking more about HVDC grids yesterday, or also connection of offshore wind.
Bit of everything.
Bit of everything. Okay.
Mainly HVDC, but
yeah. So if you have a wind farm offshore, then you want to connect it to the main grid, and then depending on the project size, on the distance to shore and so on, there's a break-even point where you don't use AC connection anymore, but you use HVDC. The main reason is that very long AC cables produce a lot of reactive power, and you can't compensate it anymore. It's just technically and economically not viable anymore. And just to give you an example, nowadays HVDC connected wind farms are mainly in Germany because they build offshore wind farms very far from shore, and what they then do is have one HVDC substation, and they connect up to 3 wind farms to it in order to match the power rating, because the HVDC converter can now be like 900 megawatt, for example, and then you try to connect 3 wind farms of 300 megawatt, and then you have a small offshore grid which is in AC, and then connected, operated by this HVDC converter and operated operated by this HVDC converter and consisting of these 3 wind farms. And break-even point is, well, I give you a big range because if you asked me 5 years ago, let's say 80 kilometers, but now we see, because there are some problems with the HVDC connected wind farms, and the risk is becoming so high that it's easier to build a very long AC cable and have some more compensations. But now there are, I think, 5 HVDC converters systems in Germany to connect offshore wind, and there are more planned. And also UK will, once they will build the offshore wind farms further from shore, they will have to connect in HVDC because it's technically easier. Okay. So to summarize offshore wind, we see we have large turbines. We operate them in the sea, we collect the power, and then we transmit it to shore. Why do we do that? Why do we go offshore? That's, and I come back to my introduction, it's because it needs a lot of space, we have higher winds over there, and also from logistics, for installation, well, we can use bigger turbines, so from this perspective it's easy, it's less restrictive, but we have some more challenges. At the moment, it's of course more expensive than onshore. That's also why you see only 8 gigawatt in Europe and 120 of onshore. But I think there is a future for this technology, and it's only a question of trying to reduce costs. Okay. Now we have 2 minutes left, and the research projects are not.
Wow.
Okay. Should I show this? I will show this.
Do you know the install capacity in North America?
Sorry?
The install wind capacity in North America? Do you happen to know it?
Do you know it?
For offshore, I know it. For onshore, I don't know it.
What's the offshore?
In offshore, it's 0.
Easy.
But Alstom will build the first 5 offshore wind turbines right now. They already have the foundations. It just, well.
So it will be 30 then.
Then it will be 30, yes. But it will come. I'm pretty sure.
Just a curiosity as well. Which are the players in the market beside Alstom? Who are your competition?
You cannot tell that, right?
No, I mean, well, for offshore wind power, it's especially Siemens, which is market leader, and which in this case not from Germany, are from Denmark, wind power sector, and Vestas, which is also from Denmark.
Bard also, right?
Areva, Bard is dead.
Is that?
Yes. And Senvion, which was formerly Repower. And now also Gamesa and Areva joined, and it's called Advent. So they're changing names all the time. So
yeah. So it's around. You mentioned around 6 names, right?
Yes.
And there were 8. Which is the one that's missing beside us?
There are 8.
Yeah, you mentioned there are 8 players in the market.
No, I was saying that
one of the
maximum is 8 megawatt.
No. I think in the previous slide you mentioned that there were 8 players in the market. I think so. It's just out of curiosity.
No. I'm just thinking. There are some others who have prototypes, but well, I think Vestas is bought now by Mitsubishi, so they are together. It's called, and it's not called Vestas anymore for offshore. It's MHI.
I remember that Vestas was near bankruptcy a few years ago, right?
No, but they're not.
They were bought by.
Yeah. But only it's a joint venture for offshore. Well, I will show this video, but okay, this is the installation of the prototype of the Alstom turbine. It's in Belgium, and we already installed one turbine onshore, of the offshore turbine, but onshore, because it's a lot cheaper to test it. And then, but they built also a prototype offshore, and mainly in order to test the foundation as well. Because this is a component which you can't have onshore.
Did you found any bombs there, or?
I don't know. So this is one of the blades, and the second one, and they pre-assemble it, and then they put it on the barge. And the third plate, then they put it once the nacelle is installed on top. Here you can see how it's shipped out, and there you already have the foundation installed. The other turbines around there are from Vestas. Vestas 2 megawatt, I think. You see how they stack together the tower? And you have the tower already. How long does it take the installation?
Yeah.
Well, for the prototype it was probably some weeks because we didn't know how to do it. But they installed a whole park in maybe half a year. And then you have also some commissioning time and so on. It takes time, but it's faster than building a nuclear power plant.
So you are an engineer at Alstom, right?
Your PhD.
I'm doing industrial PhD.
In Alstom.
Yes.
Okay, so you're not exactly employed by Alstom.
I'm employed by Alstom.
Okay, very
And
good.
not,
But I'm not out there building a turbine.
No, sure.
Unfortunately. No, I'm joking.
Yeah, go ahead.
Go ahead.
The PhD has been between Alstom and UPC.
Yes, I'm doing a PhD at UPC and I'm employed by Alstom.
But you are directly involved in research of offshore
Yes.
wind turbines?
Of offshore wind power plants.
Or you're more like
I'm-
project?
I'm more doing.
Research or project?
I'm doing nothing about project. I'm only doing research.
Okay.
Okay. Now we'll have a. If you don't mind, we can look 3 minutes
Sure.
to what are research projects we could. Yeah, we were just thinking about some proposals, and this could be part of internships, master thesis, and so on. And there are new proposals to connect offshore wind with HVDC, and basically it seems to be a step backwards because we don't use fancy IGBTs anymore, but direct rectifiers.
The onshore platform.
The onshore platform, you still need some. Not on the onshore on the onshore side, you still need a voltage source converter in order to interface the grid. But the main idea behind this, okay, I'm trying to simplify my system a lot in order to have a smaller size, and that is where you can could do some research about that. So you have here some diode rectifiers. They're connected. They could even be connected in series to build up the HVDC from several parks, and then you have the connection to the onshore platform. You have to normally the HVDC is creating the grid offshore, maybe as you know, and diode rectifiers can't do that because they're uncontrolled. So the turbines or the turbine converters will somehow have to create this grid and operate in order to push the power through control the voltage in order to push the power through the diode rectifier. I think it's quite interesting. It's in research stage. Siemens is now proposing it quite heavily, but also they haven't built it, or maybe have it built on lab scale, but not as a real project. Then another thing also in this Professor Aurelio Gomez was working on with other PhD students is to have an HVDC link, and the offshore HVDC converter is operating all the turbines. So you don't have dedicated, you have induction generators in the turbines, and the offshore converter is operating these turbines. What's the drawback? The turbines are not operated in an optimal way anymore, because they have to be all at the same speed. But you reduce a lot the converter costs, because you avoid all the converters in the wind turbines, and they are quite costly as well. Sorry. Then what I think you were asking in the beginning, what about pushing DC technology right through the collection grid and until the turbine connection? This is also one opportunity we are performing studies on that, because generally you have lower losses in DC, but you also have to see that you need some DC-DC converters. You also need some converters, some additional converters in the turbines. So, well, it's analyzed in research, but there is no real project or wind turbine which has DC output. But yeah, it's also quite interesting topic, and we're working on that as well. Then, so the turbine which you would need for that is a turbine with a DC output. How you can would think, okay, the main structure of the turbine, we don't want to change it. It's still AC generator, and then we have some rectifier here, which normally outputs low voltage DC, so maybe 1 kilovolt. But the collection grid should be at 30 kV, maybe up to 50 kV. So we need some step up. But now we can't use the AC transformer, we need a DC-DC converter. In this DC-DC converter, there are a lot of proposals, and I think there is a lot of space to study. What would be the optimal configuration for that? Then...
Here's the key thing.
Well, type 5 turbine, okay, we already talked about that.
Mm-hmm.
And some final remarks. I think I have to emphasize again, onshore is quite established, more than 30 years. Offshore is having a steep learning curve. They're learning with each project, and all the manufacturers are learning. I was showing you some research topics which can be developed in master thesis. We have quite close collaboration between university, Alstom, IREC, and so on. So there is some collaboration, and we gave you now an overview. But I think the lectures which you can have in the master, wind power and integration of renewables in the electric grid, are also quite interesting to get a little bit deeper inside, and then you can develop your research project on that.
Mm-hmm.
Yeah.
Is the wind power course focused on the electrical side of the wind power, right?
Yes.
Mm-hmm. So no gearbox.
Well, they will also explain the system, and I think it's also quite important to understand the mechanical part, but you will not end up with gearbox design. It's focused. It's part of the master in electrical engineering, so it's focused on the grid connection.
So
maybe I mean I didn't visit this. Haven't been in this course, but maybe.
Yeah, we go a bit into detail of these different parts of the the different types of turbines that we've showed you, and basically we are touching some the control scheme of the double fed induction generator, control scheme of the full power converter structure, and I mean basically Oriol is the professor who is in charge of that course, and he's working with electrical stuff. So it's focused on the electrical things, and also wind power integration, how it's done. Also HVDC is a part of that.
I mean,
it's a bit expanding what we have shown you here. And I think that I'm not sure if it's this course or it is the bachelor course, but there are other people participating on that also that can include other stuff, but mainly it's focused on that thing. Of course, you have to have some basics about beds limit and all that stuff like CP, power coefficient, pitch control, but it's focused on the electrical things.
Mm-hmm.
And integration is related with basically with the grid side converter structure of the PV panels. I don't know.
Probably also microgrids and so on.
Yeah, microgrids. And it's focused on grid side converter stuff. How do you control that? Why are you using that? Why you need them? Yes.
Okay.
Mm-hmm. More questions?
So, thanks a lot for the workshop style, for responding.